Log on, tune in, find out. Another good idea from Cambridge.
The applications to statistics. So basically I have to filter the interesting slides now. Sorry. Okay, so what I will talk about is confidence bands for non-parametric functions. Yeah. So what you think, actually let me draw this for the start. What Richard was just talking about often in statistics, what we want is we want to actually estimate a function. And that might be either the probability density function or it might come from a regression model where we do not want to make a parametric assumption, like a linear model or a specific nonlinear model, but where we want to be fully flexible. Well, if you estimate a function, let me just draw this here for a second, so maybe just univariate for simplicity. Let's say this is the true function we want to estimate, and we come up with some fully non-parametric estimate, like a kernel density estimate or a log concave MLE or whatever. And what we often, so maybe my estimate then looks like this. And then what we want, I mean, we have a point estimate of this function, that's all very well, but really we want to be able to assess the accuracy of estimation. So what we want is, we want to find, in the best case, a band that will typically be constructed around sort of the estimate we have. And then we would hope that this band would contain the true function, which I'm sort of lacking colors here, but I think it's pretty clear what we want. And we want, mathematically speaking, that this confidence, so for each point on the x-axis here, I want to basically say that it will be between this upper limit and this lower limit. I will find my true function with some prescribed probability 1 minus alpha. Just a standard confidence statement, but the object of interest now is a confidence band, which means that we want to have simultaneous coverage for all the points in an interval. And what we at the same time, of course, want, we do not only want to have coverage, because that would be easy, we just take the whole plane as my confidence band. Well, we also want that the band is sort of fairly short, because this improves the precision of my estimate. Yeah? And of course, this is a very old problem that in a way goes back to Kolmogorov, Smirnov, etc. So that is the problem. Yeah? And there are some pretty old sort of classical results how to do that you can find even in software packages like you can use extreme value theory, you can use bootstrap and so on. And some of the more theoretical work I've done in past years has given maybe a new method to deal with these things, and it's sort of interesting to see how this works and what the idea is. And I have to find the next slide. Probably this slide I know looks awful, but the main idea is very simple. Let me write this down here. So when we estimate, the centering of my band will typically be something like a kernel density estimate. So what is a kernel density estimate? In the end, it's just a sample average of my data, smoothed in a sort of useful way. So what we have is we have something like 1 over n sum f of xi. F would be perhaps some like the kernel or whatever with the bandwidth, and we have my average. And what we want to understand to construct the band, we need to understand the deviations from the sample average from the expectation. Yeah, I mean, of course, there is more to that, but that is the first step. And in a confidence band, we don't, so basically what I'm saying, at each point, I take my sample average from the kernel density estimate and I estimate the true function, and I want to understand the distributional properties of this estimate so that I can find the coverage level, okay? So, but now for a confidence band, I'm not doing it at one point, I'm doing it at all these points simultaneously. So in a sense, I have to understand the maximum over f in some class of functions that will have, you know, I won't be very specific here, but we have to understand maxima of centered sample averages. Yeah, this is something that in statistics pops up all the time, and there are tools for this, which are often called empirical process theory, which is something sort of that I've been working on. And here's a theorem that I proved with Karim Lounitzi, who was a postdoc here also in the Cambridge Statistics Initiative, which was just this year appeared in the Annals of Statistics, which looks abstract and you probably don't understand it. But there's one good idea, that this quantity here pretty much behaves for any sample size. You know, let's look at this maximum. I mean, the problem is we typically know the kernel that we have, but we do not know where we have to center because the function is unknown that we're trying to estimate. So if we wanted to compute this maximum, well, we can't do it because here's this expectation. And there's a simple symmetrization idea that says that this maximum roughly is the same as another maximum where I put here some I equal 1 to n, and instead of having the centering, I put epsilon I f of xi, where epsilon i's, what are the epsilon i's? I just draw plus minus ones at random. Yeah, it's very simple. Bernoulli random variables. You can just do this on R in your first undergraduate course. Yeah? And now this is something that you can compute, because these are my kernels. I'll show you on a slide in a second. I generate my random MyID Bernoulli variables, and I compute this maximum. And what I'm saying is effectively, this maximum, data-driven, will be the size of my band. And the question is it any good? Well, theoretically, we can prove that for any sample size, so this is not asymptotics, this is for any fixed sample size, you have a bound where this is the centered sample average. Here's the symmetrized process, sometimes called the Rademacher process, because these variables in machine learning are sometimes called Rademachers. And well, here are some deviation terms that you can work on, but that you can work out. Yeah? So the theoretical result says that whenever you have to control a maximum of many sample averages, well, one thing you can do is you just symmetrize it. This is completely non-asymptotic. It's a very simple idea. Everyone can compute it. And you have to add some trash that you can compute. Okay? But the trash here is not, you see, I mean, of course, I'm not saying that this will be very good when sample size is 100. But at least it gives you the exact dependence on sample size when you have coverage. And here's an exponential tail. So this acting on the root x is like a Gaussian tail. Okay, so this is the best you can prove in general. The question then that we sort of asked is, how do we do that? Does it work in practice, or is it just a theorem? Yeah. And okay, so let me find the next slide. Let me just show you how this works for a kernel density estimate in practice. So for a kernel density estimate, if you know the standard notation, multivariate, I just take a simple bandwidth sort of identity matrix if you want. You just have the standard kernel estimate. What is the size of the band that you put roughly? Well, you take your kernel estimate that you have to compute anyway, and you symmetrize the signs. You just put random signs plus minus 1 that you just generate on your computer. And this is a very good surrogate for what you should take as the size of your confidence band. You don't need to do any fancy asymptotic theory. You just use this and some trash I'll talk about in a second as a size. So it's very easy, and the classical Kolmogorov type results for studying limit distribution of this suprema, it's a pain and you don't really want to use it. This is a very simple way that should work for any sample size. So now we try to see how it works for any sample size. And of course, things in practice are always, let me say that this works not only, it works for kernel estimate as an RD, it works when you have a sample on a manifold, which is of interest, for instance, in astrophysics, where you have a sample on the unit sphere, which is just the sort of the sky. And you can use it in inverse problems, and this is not so much the point. I mean, I think it should be clear that this very simple idea should work in generality, and it has nothing to do with density estimation. But let's see how it works in density estimation as a test case. And there is a famous sort of test suite, the Meron-Wand test suite, that you can try sort of data on, which has all sorts of funny densities. I'll just look at two extreme cases. But what is the confidence band? You take your kernel density estimate, you add this symmetrized process, which is easy to compute. And what we did is we just took standard Bernstein-type inequality constants with root 2. So this is a very optimistic estimate for the trash in the inequality. And I cannot prove that this trash works for any sample size, but it is a heuristic choice for what the trash should be. It's not far away, but the constants, maybe I would have to put 20 instead of root 2. And then, of course, if you put, in theory, 20 for a fixed sample size of 1,000, this will return garbage. So you have to be a little bit optimistic. And when you take root 2 here, okay, so let me just look at, basically I'm going to just look at two simple cases. I'm going to look at the Gaussian density, very simple. There the method should work very well. And I'm going to look at the Claude density, which is that sort of a nasty object for a confidence band, because you need to get up and down here and you think that it's not going to work. I mean, it's for a confidence band, it's very difficult, this function, And I'll look at some others in the simulations, but I'll just show pictures for these. Okay, for the Gaussian density, what are these? It's always on the right-hand side. I don't know what happened here, but there should be. On the right-hand side, you have the standard normal density, and here you just have the convolution of the density with the kernel. So that's without the bias. This is without the bias. This is with the bias, but both of them. Let's just look at the right-hand side. This is the true function, and the band for sample size 100, 100, and 1,000. And 100 you get very wide bands, of course, but they cover it. And here you have narrower bands, which looks sort of a little better. But of course, we're not surprised that if it wouldn't work on the standard normal, then it's not very useful. I mean, it's not very surprising. What happens with this Claude density? Well, we see sample size of 100, no chance with this. But I mean, you will not find many other things that work there either, as I'll show in a second. forget the left-hand side for the moment because I have only 1 minute. But when sample size is 1,000, look at this. It looks actually pretty well. I have to say that here, if you look at it in detail, it still doesn't cover it. So there's one spike where it doesn't work. But overall, it catches the shape of this pretty well. And it's very simple to implement. You don't need any fancy techniques. And let's look at coverage simulations. And we compared it. I mean, of course, you can always find a picture where your method works well, and it's not doesn't mean anything. But what we tried is we tried to look at coverage levels, just ignoring the bias, with the classical extreme value approach, the sort of Kolmogorov-Petri-Rosenblatt, with Bootstrap, and with the new approach. And one thing that should be said, that these bands, they will always slightly overcover. So they're conservative bands in the sense that don't get the exact coverage of 95%, but slightly more. But you see that in particular for small sample sizes and also for 95 bands, you get the extremes in the Bootstrap in moderate sample sizes just doesn't work. Yeah, the coverage levels are way below 95%. So basically the bands you get from Bootstrap at the sample size of 100 or 500 are just random numbers. Whereas these things, they might give you very wide bands, so they might not be very useful. I mean, they might not be very informative, but they always cover the function. So you're sort of on the conservative side, which often non-parametric statistics, when you don't know what you're doing, is good. You can also study the average, the maximal width and the average width, but I have to stop. But the main idea is that there's a very simple idea when you have to estimate general statistics that are centered and you don't know the centering symmetrize, and the symmetrization trick will work for any sample size and usually gives good answers. Yeah? Okay, thanks.
Okay, I guess we should have time for one question.
I suppose when the function is unimodal, you might care much more, there might be a strong argument to say you care much more about coverage around the central location, about the mean.
Right.
I agree with those multimodal complex distributions. There's a stronger argument for caring more about coverage over a larger range.
Right, so generally, of course, coverage is sort of, but you can choose the band, the size of your band as you like, because when you compute this maximum here, you just compute the maximum depending on where you want to have coverage. So it's fairly flexible. But clearly, what happens in the tails, estimating a function in the tail is almost impossible non-parametrically. So I'm just looking at sort of the main features of the density. But there, these ideas actually work in a nice non-asymptotic way, so at least it seems.
Okay, let's thank Richard again.
Thanks.